Okay, everybody, welcome back. Happy Wednesday. Today is our fourth class of the semester. Today we are talking about something called the derivative at a point. The word derivative is one that we are going to use nearly every class from here until the end of the semester. So this is an important topic. Okay, so before we jump into the new stuff, we are going to talk a little bit about the first project. So here we are on page 26. And we'll spend about 10 minutes. I'm going to share with you my interpretation of this first project. And again, I said the other day that when I read this, all of this was new to me as well a few years ago. And so I created a way to think about these numbers that just kind of gave me some context, and maybe it will help some of you. So here we are. Remember, the setup of this problem is that we have two people, Ellen and Frank, and they have to decide what they're going to do on their vacation. The choices are go to the mountains, go to the beach, or stay home. And stay home is abbreviated SQ for status quo, which means keep everything as it is, stay home. All right, they have assigned numbers to their preferences for the beach or mountains or staying home. And then we have taken their numbers and we have all shifted them so that the status quo goes to what number? 0. We just translate by adding or subtracting and get them both so that at least they agree on the status quo. We'll call it 0, and then we'll look at the other numbers and analyze. And so this U, do you guys know what it stands for? What word? Utility. So utility is a word that I think we're taking here from economics. At least that's where I first saw the word utility in this context. Utility just means usefulness, right? And so the usefulness of the vacation, from my perspective, is like happiness. You could think of it as relaxation. I'm thinking of it as happiness. And if I'm going to measure happiness, I want to have units associated with it, and my units are going to be hearts, okay? The more hearts of happiness I have, the happier I am. If I have negative hearts, then I am like sadder than like normal, right? And so looking at this first row, this is Ellen's utility function. That's the little subscript E. Looking at the far right, the utility for Ellen of going to the mountains, a measure of her happiness, is 3 hearts. So we'll just put a little heart here, 3 hearts of happiness if Ellen gets to go to the mountains. If Ellen stays home, it's a 0. It's not happy, it's not sad, it's just the status quo. And if you force Ellen to go to the beach, it is a -1 heart. It is worse for her than staying home. There's like sunburn and like crowds, and you get sand all up in your bathing suit, and we don't want that. So she would rather like stay home than actually go to the beach. She is less happy going to the beach than staying home. Unfortunately, her friend Frank is the opposite. Frank really loves the beach. He gets 7 hearts worth of happiness by going to the beach. No gain or loss for staying home, but Frank does not want to go to the mountains. It will cost him 1 heart if you make him go. And so what we are trying to do is find a way to maximize the total happiness of our 2 people. Maximize the happiness of Ellen and Frank. We don't know exactly what that means yet, but we're working through that in reading this project, and there will be a clear-cut formula that we are going to maximize to try to make these 2 people jointly as happy as possible. Okay, so we translate this data into graphical stuff. So let's just take a look at this point over here, M. The coordinates of this point are 3 and -1. And that point represents the mountain. This means, Ellen is always the x-axis and Frank is always the y-axis. So this means that if you go to the mountain, Ellen will have 3 hearts worth of happiness, and Frank, who's the y value, will have -1 heart worth of happiness. That point is not an Ellen point, and it is not a Frank point. It is a mountain point. Ellen is just the x coordinate, always. And Frank is just the y coordinate, always. And so I'll just put up here like that's an E and that's an F. And then if I come over here to the beach point, it's a -1 for poor Ellen and a 7 for happy Frank. E and F always in that order. Okay? So the points do not represent Ellen or Frank. The points represent beach and mountain. All right, and that's all well and good. And so, like, if we really want to make Ellen happy, which point do we go to of the 3? To make Ellen as happy as possible, which one are we going to go to? We're going to go to M, because that's the biggest possible value in, like anywhere in this triangle, it's the biggest possible value for the x coordinate is a 3. Unfortunately, that makes Frank unhappy, and to make Frank as happy as possible makes Ellen as unhappy as possible, and therein lies the problem. So how about we do something a little bit more interesting than just say, oh, well, we're going to go to the beach and Frank is going to suck it up. We are going to propose a lottery. okay? A lottery, where we just flip a coin or roll some fancy dice and let chance determine where we go. Now, you could just flip a coin and say half the time go to the beach and half the time go to the mountains, but that completely ignores the strengths of their preferences. Like, who feels stronger about like how happy their good trip would be? Frank feels stronger. And if you just flip a coin and say 50-50, you're ignoring the fact that Frank feels more passionately about going to the beach than Ellen feels about going to the mountains. And so we're going to do something a little bit more interesting. We are going to propose a lottery. I'm just going to make up an example lottery right here. Suppose that we say, I don't know, 1/10 of the time we're going to stay home, status quo, and 2/10 of the time we are going to go to, I don't know, let's go to the beach 2/10 of the time. And then what's the last fraction? 7. It's got to be. It has to add up to 1. You're going to use that in the first question in your project. The probabilities you come up with have to add up to 1. 7/10 of the time we are going to go to the mountains, okay? This is just one possible lottery that we could propose. It's not flipping a coin. It's a little more complicated, but it's easy enough to simulate. All right, so let's figure out what this actually means in terms of the expected happiness for Ellen and Frank. Expected happiness for Ellen and Frank. Let's suppose that we just write down an equation here, a calculation for Ellen. We're going to skip the status quo for just a second. 2/10 of the time Ellen goes to the beach. How many hearts does Ellen get every time you make her go to the beach? -1. Doesn't want to go to the beach. I am going to multiply 2/10 by -1. She doesn't get -1 heart every time. It's only the 2 out of 10 trips that we make that she actually loses a heart. So it's like at the end of the day, it's like 2/10 of the outcome that she might expect when you actually force her to go to the beach. 2/10 times -1. We're going to play the same game over here with the 7/10. 7/10 of the time, how many hearts does she get for going to the mountains? That's 3 hearts for her. That's x coordinates only. That was an x coordinate of -1, an x coordinate of 3. We're going to add these guys up. We're looking for a total like expected number of hearts for Ellen. And then we'll do the status quo, although you'll see that it actually doesn't much matter because 1/10 of the time, how many hearts does she get? 0, so that's not going to affect the final value of this. Okay, so let's just get a single number. What do we get? -2, 21, 19. Tell me if that's right. Yeah? I'm asking because earlier today I failed at subtracting 9 minus 2. So is this yes? Okay. So 1.9 hearts. Here's what that means. This is just Ellen. Haven't looked at Frank. If we do this complicated lottery, 1/10 of the time stay home, 2/10 of the time go to the beach, 7/10 of the time go to the mountains. If we do this over and over and over again, I know they're only going on vacation one time, but if we just like pretend and we run the simulation hundreds or thousands of times, on average, Ellen expects that for every single vacation that they take, she is going to walk away with 1.9 hearts. On average. Is she ever going to actually get 1.9 hearts from a single vacation? No, that's not one of the possibilities. The only possibilities for her are no hearts, -1 heart, and 3 hearts. But if we let her do this like over and over and over again a few hundred times, add up all her hearts, divide by how many vacations we've simulated, on average, she's going to walk away with 1.9 hearts, okay? And you can play the same game with Frank. We'll do this one a little bit quicker. These are now all Frank numbers. 1/10 of 0, and then 2/10. It's the same probability, same lottery, but now it's Frank's number. So what's Frank's beach number? 7. And then plus 7/10 of the time, his mountain number, -1. 14 minus 7, 7/10. So 0.7 hearts for him. Okay, so he's not as happy as Ellen is at the end of the day, but that doesn't mean this is an unfair lottery. Remember what we're trying to do. We're not trying to make them equal. Nobody said equal. We said like the joint happiness is supposed to be as big as possible. And maybe 1.9 for Ellen plus 0.7 for Frank. Maybe that's the best that we can do, okay? I'm not saying it's the best one, but every single lottery corresponds to some expectation for the average number of hearts for these two folks, and you are going to maximize the joint happiness but we haven't yet read what that means in terms of a formula, right? And we'll just finish this with one more thing in the picture. Okay, so if I plot a point where ln is at 1.9 and Frank is at 0.7, remember ln is always the x and Frank is the y, so I'll go to 1.9 and 0.7. I think I land somewhere around there. So this is 1.9, 0.7, ln and Frank in their usual order, okay? That point is the one that represents this lottery that I just made up. 10th of the time stay home, 2/10 go to the beach, and 7/10 go to the mountains. And actually, there's like some geometry happening. This point right here is a weighted average of the three corners of my triangle. It is pulled 1/10 of the way towards the status quo. That's not very far. It's not really pulled in. Like it's pretty close to being on that long line, but we're pulling it in like 1/10 of the way, just a little bit toward the status quo. Which one is it closer to, beach or mountains? Mountains, because we weighted the mountains much more. Look, mountains is 7/10. Beach is only 3/10, so it is pulled much more strongly towards the mountains, but still some pull towards the beach. Every point in and on that triangle is a lottery. We're looking for the best point, and we haven't clearly defined yet what best means. And so the very first question in your project, has it been officially assigned according to the suggested calendar, or we? Yeah, the 2.5 comma 0 is find, find, so 2.5 0 is this guy here. Find the lottery, find the probabilities. Well, okay, so I started this problem with probabilities, and I found the final point of 1.9 and 0.7. You're doing the same problem, but in reverse. They're telling you the final point is this 2.5 comma 0. You're going to call the probabilities like P and Q. You can bring status quo in there if you want, but because it's all zeros, it's not going to affect the calculation. So same idea, same kinds of equations that I've got up there in purple and orange, but just changing where the knowns are and where the unknowns are. Okay, any questions on that? All right, so for feedback for me for teaching this course in the future, is this a good use of 12 minutes, 10 minutes of our time? Is this helpful in terms of the reading? Okay, good. All right, so let's jump in now back to where we were. All right, number one, everything that we've done with velocities over the last two classes can be applied to arbitrary functions. So remember we talked about the zombie race. So these guys were just running, stumbling at a certain speed, and then we tossed the ball off of a tower and the ball was falling faster and faster and faster. So it's all been velocities, but we can apply all of our formulas from velocity land to arbitrary functions, not just the height of the ball or distance functions for our zombies. So for a general function, instead of average velocity, we're just going to call it average rate of change. We're just making a more general statement here. And instead of instantaneous velocity, we'll call it instantaneous rate of change. So instantaneous rate of change, there's a fancy formula here, but I'm hoping it's starting to look familiar to us. We have seen this thing right here. I will point out that this right here is the slope of a secant line. Slope of the secant line is just the fraction part. And then when we incorporate the limit, what does that secant line turn into? Tangent line. So the whole thing becomes a slope of a tangent line. Okay, and this picture we've seen before, but now it's going to be labeled slightly differently than before. So we're going to try to connect those crazy symbols to this picture. The idea here, I've got my red point, which is fixed. It's a comma, whatever the y value is, f of a. And then I've got this varying point. It's over here in green. So here's my a down here on the x-axis. And then we're just going to take that point, and we're just going to move over a little bit until we land on another point. And we're calling that distance that we move over h. So everybody okay buying a plus h is, you were at a and then you move h over. And what I really want is to take this secant line and turn it into a tangent line. That's what we're after. And so that means keeping the fixed point fixed, but taking this varying point, sliding it along the curve until you get as close as possible to that fixed point. So we did this the other day on Geometry Sketchpad. And what are we really doing to h in order to force this point to get really close? Making h smaller towards what number? 0. Okay, so that's this piece right here. Limit as h goes to 0. And then the rest of the calculation, this big fraction, well, that's just the slope of this line, this blue line that's drawn in here. You just do the calculation. This is the slope. It's change in y over change in x. Change in y is just the, we'll say the y down here, which is f of a plus h, minus the y up here, which is f of a, just subtracting y values, over, okay, this has already been simplified, but what was it if you subtract the x values? A plus h minus a. And then the a's always cancel, right? So it's been cleaned up a little bit. Okay, so next page, we'll do a concrete example. This one's from your book. The population, f of t of China, in billions, this is billions of people, can be approximated by f of t equals 1.267 times 1.007 raised to the t, where t is the number of years since the start of the year 2000. So let's get our hands dirty with some pre-calc, and then we'll do some calculus stuff. So first of all, what kind of function is that? Linear, quadratic, exponential is good, because we see a number raised to a variable power, so that's exponential. Next question, is it exponential growth or exponential decay? Growth, what do you see in these numbers that tells you growth? Higher than 1. That 1.007 is bigger than 1, therefore growth, because 1.007 is greater than 1. And continuing to analyze that 1.007, what is the growth rate as a percentage? 0.7 is good. We know that the growth rate, I forget the letters, like maybe something like 1 plus r. And so that is the, like if you can find the r, you have found the growth rate. And so the r is 0.007, but as we write that as a percent, 0.7%. So the population of China is growing by 0.7% per year every year according to this model. Okay, let's do some calculations. Part D. What does the model predict for the population at the start of this year? Okay, so here's my formula. T is the number of years since the start of 2000. So the start of this current year, what am I plugging in, and for what, where am I plugging it? 17 for T, yeah? Okay, not everybody has to do this, just 1 or 2 people is fine. But f of 17 is what we're after for the first part. And then how about at the start of the coming year? F of 18, all right, so can somebody who's not already doing the 17 calculation do the 18 calculation? So we're just typing into a formula. We'll get a couple of numbers and then we'll write them down. Who's got it? Six, 5, okay. Anybody got 18 for us? Okay. So again, the units here were billions of people. Is there an abbreviation? Maybe that. So at the start of this year, predicted 1.4265 billion people in China. At the start of 2018, 1.4365 billion people. Okay. So it looks like, how many people did we gain in millions? How about we do that? 100 million, is that right? I don't see it as 100 million. 10 million is what I see. Yeah. So, okay, so it looks like about 10 million people more in China at the start of 2018 than the start of 2017. Suppose that we go one more year. I'm not going to do the calculation for 2019, but suppose we did. Would you expect it to be another 10 million people on top of the 2018? And if you don't expect it to be 10 million, do you expect it to be more or less than 10 million? And it's going to be more because it is exponential, and we know that those guys grow faster and faster, right? But Lucas? Yeah, and so when we do this 0.7%, we're not doing it on the 1.4265 value, we're doing it on a bigger number. So we're taking the same 0.7%, but of a bigger starting population, so we'll expect a little more than 10 million new people in the year after, and every year grow a little bit more. Okay, now we'll answer the calculus question right here, part E. It says, what is the growth rate at the start of this year as an absolute amount? Said another way, estimate how fast the population was growing at the start of this year. How fast the population is growing at the start of this year. If we just look at the two raw numbers that we have, we see about 10 million more people over the course of the year. But that growth rate, 10 million people per year, is looking at a very long time frame. And so it would be more accurate if we cared about what was happening January 1st, 2017, just at that one moment in time, instead of, okay, so 10 million people per year is an okay starting estimate, but 1 year is too long. Maybe we should look at like just what happens between January 1st and January 31st. Just look at a month and then maybe extrapolate it for the whole year. Or maybe just look at 24 hours in the first day of 2017 and extrapolate it for the whole year. So that's what we're after. It's not going to be too far from our 10 million people per year, but to get a more accurate answer, we have to hone in, just like we've done in a couple of different examples this semester. So here we go. Suppose that we do f of, okay, so how about we start at like 17.01. Let me write this in the content. I'm going to rewrite your formula from before first. F of a plus h minus f of a over h as h goes to 0. This is our calculation. We'll use that formula a bunch in the next week or two. I'm not going to write the limit for right now. I'm just going to start over. How much is the particular a value that we care about? Yeah, 17. It's the start of 2017, so that is just plain 17, and then plus a number, yeah? And then minus f of what number? 17 is right there. And then we get to divide by h, right? Now let's plug this stuff into our particular formula. Blank fraction, put a subtraction symbol. F of 17 is the easier piece. I'm going to start there. So our calculator people typed this in already, but even if you didn't, we can write some stuff. What is f of 17 symbolically? 1 point, no, I don't want that number. I want the actual, like what did we type into the calculator? 1 point, there was a number before that. What was the 1.267 times 1.007, and it's supposed to be to the t, but now it's to the 17, right? Like that's what our people typed into the calculator. So that's f of 17. I'll highlight so we can keep the stuff straight. So that guy is that guy. And then f of 17 plus h, this is the tricky part. Some people would say, oh, f of 17 plus h, that's just this thing that I wrote down plus h. It's not, don't write that. It's never that. What that means, f of 17 plus h, is that we are replacing the t with 17 plus h. So it is 1.267 times 1.007 to the what? 17 plus h. That's it. You are substituting, replacing t with 17 plus h. We're not adding h at the end. Okay, so this piece right here is now this piece right here. And then I'll copy my h on the bottom. Okay, and I didn't write that limit, but the limit as h approaches 0 is the final piece of this calculation. Now, last class we talked about how maybe we can do some algebra to like clean the thing up and cancel some stuff and then magically just be able to plug in 0. We can't do that in this example, or at least it's not worth our time to do here. But if we try just plugging 0 in now, what happens? Division by 0, and what happens on the top? It's also going to be 0. Plug 0 here and you get this thing is the same as this thing. Okay, so we're going to use the calculator. You don't need to do this on yours. I'm going to do this real quick. But I'm going to type this complicated thing one time. This is pretty powerful. So I need parentheses here. So 1.267 times 1.007 raised to the 17 plus, I'm going to call it x instead of h here. I think that's good. And then subtract off 1.267 times 1.007 raised to the 17th, all divided by what number? Divided by, yeah, x instead of h. And the power of putting that in here is that then, I'll make sure this is on ask, then I can go into second table up here in the top right, and I can type in any h's, it's x here, but I can type in any h's that I want. And what kind of h's did we want? Really close to 0. And so, okay, so like for example, I could type in like 1. H equals 1, that's 1 year. That number is really close to the 10 million people that we saw before. In fact, this is a more accurate answer. Like I didn't write down very many digits at the top of the screen, but this is the 1 year number. If you look at the start of 2017 and the end of 2017, that's how many people the two things differed by, the populations differed by. But 1 is a really long time, so how about we try 0.1? And we try 0.01, and we try 0.001, something like that. For kicks, we should also approach from the other side of 0. Negative 0.01, something like that, and negative 0.1. Okay, so looks like we've got a pretty good sense of our estimate, but remember, if you highlight over here, you do get more digits, right? So like looking at the bottom, we can see more digits. So I would say my answer is like, you know, one of these two numbers, or maybe average them if you're feeling very fancy. Okay, so can somebody write down, just write down, we'll just use this number here. So this is our best guess. 0.00995. 0812, I don't know how many to write. Okay, so as h goes to 0, our, I'm going to call it DQ, that was difference quotient, which is this thing. Difference quotient approaches somebody 0.0099. Okay, and then we'll get some units here. It's not just billions of people. This is a growth rate, billions of people per year. Billions of people per year. And we're not just making those units up. They don't come out of a hat. They are this fraction. What are the units for my numerator? This, you know, when we typed in this green thing, we got 1.4265 billion people, right? So it's just people minus people. It's still billions of people on top. What are the units for H? What was H? H was the time. What are the units? Years. Okay, billions of people on top, over, years on the bottom. That's what the units are. Okay, so there's our estimate for the instantaneous rate of change of the population at the start of 2017. It's not exactly the same 10 million people that we saw, but we were looking at a full 1 year time period. That was too long. So at the moment the clock struck midnight at the start of 2017, this was it. If you wait 10 seconds later, that number is slightly bigger. It's exponential growth. The growth rate is getting slightly bigger every time you take a step to the right. But at the one instant at the start of 2017, that's our best guess. Okay? All right, next page. Okay, and this thing, which we just wrote on the previous page, it's our difference quotient with that limit in the front. It is called the derivative of the function f at x equals a. The derivative of the function f at x equals a. Note that the independent variable will usually be x, so we'll probably just use x instead of t. Doesn't much matter, it sort of depends on the context of the problem. And that calculation with the limit and the difference quotient is denoted f apostrophe of a. And that little apostrophe is read as a prime, f prime of a. So our most important definition of the entire semester is this one right here. It says that the derivative at a particular number a is denoted f prime of a, and it is this thing with the limit and the difference quotient. And so, for example, back in that China population question, f prime of, what was the specific input number we were interested in? 17. And we got 0.009985, is that right? So we got that guy, and that's our equation. Is that that means that the derivative at 17 is this 0.009985. A little bit of vocabulary. Finding the derivative of a function is known as differentiating the function. And if a function has a derivative, the function is said to be differentiable. Soon enough, we'll see some that don't, but for the beginning here, everything that we talk about is going to have a derivative. Number 5, we have already seen today and in earlier days that this fraction is the slope of a tangent line, slope of a secant line, and it is the average rate of change of a function. And when we slap that limit as h goes to 0 in front, the slope of a secant line becomes the slope of the tangent line. And so we can have a quick geometrical look at that slope of tangent line thing. Will probably look kind of familiar. Here we go. Okay, this green thing is the function f of x equals pi times x squared. So just a parabola with a pi in the front of it. And at the moment, I've got a special point over here, which is right around x equals 2. And then I've got this lemming. So the theory is that like lemmings just like follow each other, right? And so like what I want is this lemming to go follow what? The special point, right? I want that lemming to just walk over and follow the special point wherever the special point is. So thinking about this special point, can you guys envision the tangent line? Is it uphill or downhill at this special point? The tangent line, so this currently is a downhill secant line, but the tangent line, which is not pictured right now, is roughly here. Okay, so it is uphill, and we know that the slope of the tangent line is this derivative that we've just talked about. And so if I just ask the lemming to move and land on the special point, there you go. And what this means is that the derivative of this green function at x equals 2 is what number? 12.62. The derivative is the slope of the tangent line. Derivative is the slope of the tangent line. If I were to move my special point, say someplace over here, I don't know, -6, something like that, uphill or downhill tangent line? Downhill. So is the derivative at -6 going to be a positive or negative number? Negative. The derivative is the slope of the tangent line we can move. So, okay, the derivative at -6 is right around -37 and change. Just thinking about magnitudes, the slope that we had over here at x equals 2 was about 12. Does it make sense that this is a bigger, I mean, it's negative, but does it make sense that it's a bigger number? Yeah, it's steeper, right? And so we can say as you run to the right, like your tangent lines are going to get bigger, and they're also going to get bigger on this side, but in a negative way. Okay, so coming back here. This statement is super important. The derivative of a function at a point is the slope of the tangent line of the function at that point. So we're going to do like this kind of like call and response thing real quick. I'm going to read the non-bold, and you're going to read the bold all together. It's going to be awesome. Here's the Cliff Notes version. The derivative is the slope of the tangent line. Some of you did not repeat. We're moving on. In case you missed it, everybody, the derivative is the slope of the tangent line. One more time with feeling. The derivative is the slope of the tangent line. Yes, it is. All right, moving on to the next page. Jump in with the group activities. I will walk around.